I know that at this point, you're probably dying to know where KACA and KBCB came from. And this is where I let you know that it's entirely possible for you to derive it yourself. And you derive it from the Rice expression. So let's go ahead and do it. Here is a compound, HA, goes to make H plus and A minus. It must, according to the Rice expression, have a starting amount of A and no H plus and no A minus. Well, I'm going to have some of my HA go away. But not all of it's going to go away. Do you know why not all of it's going to go away? Because if I remember how this worked, if I throw a bunch of HA into solution, oh, by the way, this is a joke. You ready for the joke? What is this? A barrel of laughs? Get it? Anyway, if I throw a bunch of HA into solution, pretty much all of it stays as HA. I've started with 100% of it and is still almost 100% of it. Maybe a little bit becomes H plus and A minus, but certainly not all of it, which means that while I'm not sure how much of it is that goes away, it's not 0 and it's not 100%. It's some value x. The amount of H plus that forms is plus x. The amount of A minus stoichiometrically that has to form is also plus x. So this becomes C minus x, x, and x. There, I've actually got my amounts at equilibrium. Notice how this is very similar to when I was doing my solubility product stuff. The only difference is that then I didn't count any of this because it was a solid. Now I've got to count it. It makes the math a little bit tougher. So Ka is equal to H plus times A minus over HA is equal to, let's see, x times x, because that's what that is. That's what that is, over C minus x is equal to Ka. So, got this here, Ka is equal to x squared over C minus x. But x can be equal to H plus. So that means that Ka is equal to H plus squared over C minus H plus. Now at this point, you have what is known as a quadratic equation. It's an equation which has this second order polynomial here. And I can rearrange all of this to have this great big polynomial I have to solve. And I can do it with a quadratic equation. I can do it by back substitutions, all of that sort of thing. But I'm going to teach you a bit of cleverness here. It's kind of neat. Watch. See that H plus right there? How big is that amount? I mean, let's compare it to the amount of C that I started with. If I started with 1,000 C's, how many H pluses were formed? Well, not very many. In fact, were so few formed that I can ignore them. As a matter of fact, I bet I can. And if I ignore them, if I make the assumption that they don't matter, then I can get rid of it. And if I get rid of it, then my Ka is equal to my H plus squared over Ca. And then when I rearrange it, my H plus squared is equal to my Ka times my Ca, which means that my H plus is equal to my Ka times my Ca, when I run through here with a square root, to the 1/2. I have derived the weak acid-base equation from the Rice expression by simply doing my legitimate substitutions of everything in, putting it all in terms of one variable, and then making a single assumption. I'm making the single assumption that the amount of X, the amount of dissociated weak acid, is small because, after all, it is weak and therefore doesn't dissociate much. And once that X goes away, then I now have a polynomial that I can solve just by taking the square root of everything, and I end up with this nice simple expression, which is my weak acid, weak base calculation expression. I can do exactly the same thing with the base. Exactly the same thing happens. Instead of Ca, I have Cb, but I still make the same assumptions down here, and I end up with OH minus equals KBCb to the 1/2.